Hello and welcome back. Today I am going to be answering question 1.2 of section 1 of algebraic geometry. So I think we should just start. First, let us note that this is the question, however I'm not going to do it in the order that it's given, just because I can answer other parts much more easily first, and then with those answers I can answer the first parts. So, let us note, I have chosen the wrong color, note that the function z minus x cubed and y minus x squared both vanish on all points within y, so are within the vanishing set of y. Sorry, the ideal generated by y, generated by functions which vanish on y. Now take f within that ideal. Uh, as k adjoint x, y, z is a unique factorization domain, it is also a Euclidean domain. So we can perform the Euclidean algorithm on it with f equals q times z minus x cubed plus r, where q is in k of x, y, z, and r is in k of x, y. Let's give these indices 1, because we're going to do that again with r. So, again, r equals q2, let's do that, multiplied by y minus x squared plus r2, r1, where q1 is in k of xy and r2, not q1, q2, and r2 is within k of x. Thus, f equals q1 times z minus x cubed plus q2 multiplied by y minus x squared plus r2, where r2 is r2 of x, let's just say, dot and dot. Let's make them bigger. So, let's take p in y, where p is just t squared, t cubed. Well, let's f in our ideal means that f of p is equal to q1 times 0 plus q2 times 0 plus r2 of t is equal to 0 for all t in k. It is one of the premises of algebraic geometry that we're working over a algebraically closed field, and therefore algebraic closure implies that it's infinite, which then implies the following result. As r2t equals 0 for all t in k implies r2t equals 0 is just equal to 0. R2 is equal to 0. This is not true for all fields. For instance, the finite field F2, well, x believe there are definitely polynomials which are always 0. X squared minus x. Plug in 0 and it's just 0. Plug in 1 and it's 0. So it's 0 everywhere, but it's not itself 0. So f equals q1 times z minus x cubed plus q2 times y minus x squared, which means that it's within the ideal. Generated by z minus x cubed and y minus x squared, which we have said that those generators are elements of I of y, so this is a subset of I of y, but any element of I of y is within there, so it's also a superset. I of y is a subset of it, minus, comma, y minus x squared. So the two are equal. I of y equals z minus x cubed y minus x squared. Therefore, we have found the generators of I of y, which are z minus x cubed and y minus x squared. Now, let us turn a page, metaphorically, and I will write 1.2 up here, and consider the function from k of x, y, z into k of x via f of x, y, z maps to f of x, x squared, x cubed. No. I have wrote this wrong in my notes. My apologies. Well, yes. I should probably not use the same variable twice. Sorry. T goes to f of t, t squared, t cubed. We have literally just proven that the kernel of this map is this, which is this. Therefore, the kernel of this phi is z minus x cubed, y minus x squared, because it's by definition the vanishing set of functions of this type, or it's rather every function of this type where this is equal to 0. Every function where this is equal to 0 is I of y, which is equal to this. Therefore, we have the following short exact sequence of k modules. 0 into I of y into k of x, y, z, and this is just an inclusion where I takes I of y into k of x, y, z via f of x, y, z maps to f of x, y, z. This is very obviously injective, so it's exact here. Now let's do this again. K of t into 0. This is surjective because, well, f of x, 0, 0 equals f of x for any function x. So this is surjective, and the kernel of this is the image of this. Therefore, this is a short exact sequence of k modules, which means that that k of t is isomorphic to I of is isomorphic to k of x, y, z over I of y equals A of y, the affine coordinate ring. Therefore, we have just shown this. Now, an ideal is prime if and only if an, an ideal of a particular ring is prime if and only if its quotient ring is is an integral domain. K of t is an integral domain, therefore I of y is a prime ideal. Therefore therefore y is a variety. Therefore y is a variety as k of x, y, z over I of y is a domain. Now, finally, we use, well, this is because of the Nullstellensatz, corollary 1.4. Now, finally, the dimension of a variety or an algebraic set is the same as the dimension of its affine coordinate ring equals the dimension of k adjoin t equals 1. Therefore we are finished. QED. This was a very short one, so thank you for watching. Oh, I should thank you for watching. As I said yesterday, I am certainly not as good a drawer or an artist as my wonderful fiancée, but we make do. Goodbye.